Good day and welcome back for part one of our discussion on implicit differentiation. Before getting into any of the applications of differentiation that we are interested in, we need to make one more quick pit stop and discuss something called implicit differentiation, which we will immediately put to use in our next section when we get to related rates problems. Now, the key idea is that up to this point in time, all of the functions that we have encountered in this class, especially the ones that we have differentiated, have been written in an explicit form. That is to say, something along the lines of y equals f of x. The dependent variable y is expressed explicitly as a function of that independent variable x. And for some simple examples, we've encountered things like y equals 3x plus 1 squared, or maybe something like y equals cosine x squared over the square root of x. These are just random examples of an explicitly defined function. And when it comes to differentiation, we have no problem whatsoever differentiating functions in this form. Based upon the function itself, whether it's a product, a quotient, a composition, we have a corresponding or an associated rule of differentiation that we can apply. But as we'll see, we have to be a bit more careful if it's an implicit equation. So what do we mean by that? For example, x squared plus y squared equals 1. If we think about this for a moment graphically, it represents the equation of a circle that has radius 1 and is centered at the origin. So roughly speaking, we're thinking something that looks kind of like this. But the key observation that I want to make is no matter how hard we try, I cannot explicitly represent one of these variables as a function of the other. So note, if we want to think of y as being our dependent variable, we can write y squared as 1 minus x squared, and very quickly write y equals plus or minus the square root of 1 minus x squared. And note, in order to write this as a function, so in this case we have y equals, say, the positive square root of 1 minus x squared, that would be a function. Or if you were to isolate and say y equals minus the square root of 1 minus x squared, that would be a function. But in this form of plus minus, every input has two corresponding outputs. So we cannot explicitly represent y as a function of that independent variable x. Now note, graphically, the positive square root portion refers to the top half of the circle, and the negative refers to the bottom half. So when it comes to an equation of the form x squared plus y squared equals 1, the question we might want to ask is, can we still find dy dx? And the answer is absolutely. We're just going to have to use what is called implicit differentiation. So let me build up to what it is we mean by implicit differentiation by investigating a few examples that kind of progressively build in difficulty. So to start, if we have something like the derivative of x cubed with respect to x, the key observation is to note that it is a function of x. We want to differentiate it with respect to x. Those two variables agree. So this is a normal explicit derivative. So we would differentiate this exactly as we normally would with the power rule. But if we make kind of a small subtle change and we now say, how about we differentiate y cubed with respect to x? The y and the x disagree with each other. So this would be what we consider to be an implicit derivative. And whenever we're calculating an implicit derivative, what we're assuming is that the y is actually a function of x. And we're trying to differentiate this. And how would we differentiate something of this form? Well, we would go back to our previous section or topic with the chain rule. And we'd say we differentiate the outside function. We substitute in the inside function. And we multiply by the derivative of that inside function. And this is actually what an implicit derivative is. We differentiate that y cubed, focusing back on the left here, exactly as we would like to, 3y squared. And because it's an implicit derivative, function of y with respect to x, what we need to do is multiply that by dy dx. And the dy dx could also be replaced equivalently with just a y prime if you prefer that notation. And note, it's nothing more than the chain rule in disguise. But the general rule of thumb, whatever that function of y is, and you're differentiating with respect to x, you differentiate it exactly as you would like to, 3y squared, and then because it's implicit, you multiply by a dy dx. Now, when it comes to implicit differentiation, we can combine all of our previous rules. For example, we could have things involving the product rule, quotient rule, chain rule. So let's look at a few more examples. If we want it to differentiate x times y squared, what we must observe is that this is really a product rule. You have one function x multiplied by a second function y squared. So the product rule tells us that we differentiate the first times the second plus the first times the derivative of the second. And this gives us two derivatives that we need to evaluate. Note the first one, the derivative of x with respect to x, that's just an explicit derivative. And in this case, the derivative of x is 1 times y squared plus x times the derivative of y squared. And this is an implicit derivative. Y is a different variable from x. So we differentiate the y squared exactly as we want to, 2y. And because it's an implicit derivative, we multiply by dy dx. And the idea is exactly the same if we have something like, say, sine of xy. It's just to get started, we are going to have to use the chain rule. So what I'd like you to do is to pause the video for a moment and see if you can calculate this derivative. So assuming that you've done that, and if you haven't, you really should, to differentiate this, we'll use the chain rule. So we think we take the derivative of the outside function, cosine, we evaluate it at the inside function, and then we multiply it by the derivative of the inside function. And when it comes to differentiating the inside function, we have x times y. So that is a product rule. So writing this out step by step, we would have the derivative of the first times the second plus the first times the derivative of the second. And then just working term by term, or in this case maybe derivative by derivative, the derivative of x is 1 times y plus x times the derivative of y. And let me just think about this to the side for a moment. If I want to differentiate y with respect to x, this is an implicit derivative. We have y with respect to x. So what that means is we differentiate the y exactly as we would like to, 1, and because it's implicit, we multiply by dy dx. And intuitively, this is exactly what you hopefully expected. Note, d dx of y, the derivative of y with respect to x, all that's occurring is that the y gets grouped in the top with the d. So it becomes dy dx. So hopefully this gives us an idea of how we can differentiate something implicitly. Let's now shift over to the type of problem that we will typically encounter. The typical problem we encounter is going to be similar to the example that we see. We're going to have some equation involving x's and y's, and what we would like to do is find dy dx. And for this type of problem, it turns out that there's a nice procedure that we can follow. That's not always the case in calculus and mathematics, but it's certainly the case for these implicit differentiation problems. And it's a simple idea. You differentiate both sides of the equation with respect to x. You're going to have some number of terms involving dy dx, so you group all of those terms to one side, and then you isolate them. Stated as simply as possible, you differentiate with respect to x, and then you solve for dy dx. So let's go ahead and see how we can put this to work. So we have this equation, y cubed plus y squared minus 5y minus x squared equals minus 4. And this is one of those examples where we cannot explicitly solve for y in terms of only x's. So we are going to differentiate implicitly. So we differentiate both sides with respect to x. The derivative on the right-hand side is maybe the easier one. The derivative of a constant is always 0. On the left-hand side, we need to just differentiate term by term, and the first 3 derivatives are going to be implicit derivatives. So working out each one individually, we differentiate that term exactly as we would like to, so 3y squared for the first, and we multiply by dy dx. Similarly, 2y dy dx minus 5 dy dx. And finally, when we differentiate minus x squared, we think minus 2x. And this is the calculus portion of the problem. What remains now is a bit of algebra. We have some number of dy dx's. Well, here there's actually 3 of them. So we are going to group together all of those dy dx terms. 3y squared plus 2y minus 5. And then we'll take that minus 2x term and we'll go ahead and add it to both sides. And then finally, dy dx is now something we can solve for. So we've just algebraically isolated it. And what we now have is dy dx, which we have found using implicit differentiation. And it's worth noting that this looks different than dy dx typically would look for us. In the past, it's always been just a function of x. But the original equation, we were unable to solve for y as a function of x. So it's not unexpected that the derivative dy dx would also involve x's and y's. So you may be wondering, what's the geometric or graphical interpretation? So let's think about what's going on here graphically as well. Note, the derivative, as it has all semester, is going to represent the slope of a tangent line at a point. So we still have that same graphical or geometric intuition. And if you wanted to know what the graph of a curve, such as the one above, would look like, it's this equation that we see below. And in order to graph something like this, there's many different kind of freely available online programs. One program that I find particularly nice for visualizing graphs is called GeoGebra. So the geo is kind of geometry, gebra is from algebra. And if you type GeoGebra into Google, you can find this program for free. You can get a version that you download onto your own device. You can get an app that you download onto your smartphone or tablet. And they even have an internet version that you can use just online. So definitely worth looking into if you need a bit of help visualizing a curve. So let's go ahead and investigate this example from that graphical perspective. We have the derivative above that we have found. We have a graph. Let's just see if we pick some points on the curve, what the slope of the tangent line would be, and hopefully they kind of match up with our intuition when we actually sketch them. So if we start at 1, 1, and I want to know what is the slope of the tangent line there. The slope of the tangent line at 1, 1 is the value of the derivative at that point. And I want to indicate something and emphasize it in terms of notation. If you have an expression that you want to evaluate, what we will do is put a vertical bar, and then we will subscript it with the point that we want to evaluate it at. What I do not want you to do is abuse notation. If you were to write dy dx equals some number, that would be incorrect, because dy dx is this more general representation involving x's and y's. What we are about to find is dy dx when we substitute in x is 1 and y is 1. And when we do that, we would get 2 times 1 over 3 times 1 squared plus 2 times 1 minus 5, which is 2 over 0, and that's not a good thing. That means that the slope of the tangent line at 1, 1 is undefined. And let's think about why that's the case. On our graph, 1, 1 has a tangent line which is vertical. So now things are making more sense. If it is a vertical line, it has an undefined slope. Let's go ahead and calculate one more just to make sure our intuition still agrees. If we found the slope of the tangent line at the point 2, 0, so remember this notation is telling us replace each x with a 2 and each y with a 0. When we do that, we will get 2 times 2 over 3 times 0 squared plus 2 times 0 minus 5. And the slope of the tangent line at the point 2, 0 is minus 4/5. So graphically, if we go to that point on our curve, 2, 0, and I roughly sketch in the tangent line, note the slope of this tangent line is the value of the derivative at that point, which is equal to minus 4/5. And intuitively, yeah, that's a line with negative slope. That's roughly somewhere around 1. So minus 4/5 makes perfect geometric sense. And finally, for this third point, 1, minus 3, I will let you do the arithmetic, but when you substitute that into our formula above for dy dx, you will find that the slope of the tangent line there is 2 over 16, or I guess we could write 1 over 8. Now, one other small thing to point out is it's not always easy to find a bunch of points on one of these implicitly defined curves. But for example, what you could do is just substitute in a certain or given value of x and then solve for what those corresponding y values would be, which is what I've done here. So that finishes our introduction into implicit differentiation, and our remaining videos will explore several related examples. So stay tuned and take care.